real life problems. So, mathematics is considered to be the cosmic eye of science and humanity. So, the simple reason is that see, if you have huge set of data, you can compress data and talk in terms of simple terms like functions. Suppose you want to talk about temperature profile in data. So, you can't actually keep measuring temperature at several points. So, even if you did, you can't give this set of data at every hour and a list of 10 values or 14 values. On the other hand, if I say the function is cos x or sin x or something, you will immediately understand what kind of behavior is there. So instead of handling data, you can compress information in terms of simple quantities like functions, differential equations, etc. So that is why it is considered to be the cosmic eye of science and humanity. Why it is, I hope to convince you in the next slides, few slides. It has a lot of applications, starting from algorithms of computers, how the brain functions, and so on. It goes on till structure of DNA, encoding data, and calculating data. In fact, just a few days back, I came to know that treating cancer, for instance, suppose you have a cancerous tumor, let's say in the lung, and you want to use some radiation to melt that tumor. So earlier what they used to do is give radiation to the entire lung. Okay? And so that could damage many things. But today, because of technology and mathematics, you can target the radiation just exactly on the tumor part of the lung. For instance, what they will do is they'll take the patient, mark coordinates on that, and then make a scan, and based on the position of a particular several parts of the body, they are able to pinpoint where exactly the lung is, where exactly the tumor in the lung is, and then by giving radiation just on the tumor, you can make a safe radiating therapy. So there are so many applications of this which we don't come across in our class curriculum and so on. So one simple way of, or amusing way of doing this, thinking that why mathematics is important these days. Everybody talks about information technology, data science and all. So let us see what kind of tools people were using in the different world wars. So in World War I was all about chemistry, because people invented the nerve gas and many people were releasing the gas and trying to kill the soldiers. And World War II was all about physics, because they then were able to master the nuclear reactions, and then they dropped the atom bomb, where. And so that was it. Today, you can easily guess if there is another war, it will all be mathematics. So the guy who knows, the country which will know the mathematics and is able to master that, as I already told you, if you can locate the tumor precisely inside the lung, you can also locate where exactly a particular facility is there so that you can target it. So let me give you, this is not an exaggerated imagination. It has already happened actually. See, for instance, this is called the Patriot missile failure. So you guys are not one except for one or two. I don't think nobody ever knows what this war is about. In 1991, what happened was Iraq invaded Kuwait. See, if you look at the map, Iraq is such a huge country. It is, you can think it is just like India and Bangladesh. So one fine day, Iraq decided that Kuwait should be a part of Iraq, and they invaded, and there was a war between Iraq and Kuwait. So obviously US is the big brother, so they immediately came down and wanted to fight the Iraqis. So they were trying to use the missiles. Now, Iraqis had a missile which was built in the 1950s, given to them by Russians. So it is like our Diwali firecracker. You just launch it, just guess where your target is, and then launch it. Whereas Americans had a missile called Patriot missile. So this was developed in sometime in the 70s and 80s, and it was a state-of-the-art missile. And what it had was an onboard computer. So onboard computer, what it will do is, it will target the enemy missile and then locate its position vis-a-vis itself, and then make sure that it hits the enemy missile precisely. Just like I told you about tumor and lung tumor and giving radiation like that, you can also target your enemy missile precisely, and then this missile will go and attack it and destroy it. But then, what happened, you can guess, that it always, the primitive missile was the one which succeeded, and then it killed 28 soldiers, injuring 100 others. So even though that missile was advanced stage, it had an onboard computer, it could not hit the target. What is the reason? The reason is mathematics. Because when you switch on the computer on the missile, it turns out that inaccurate calculation of times is due to computer arithmetic errors. One thing you must understand is, on the computer, it can only store finite information. We all studied what are real numbers, and it includes rational numbers and irrational numbers. So what is the basic difference between rational and irrational number? Here, rational number, you can compress it in terms of a fraction. Suppose you have a decimal expansion which is periodic but repeating, that means repeating, then you can represent as a fraction. But if it is non-recurring and non-terminating, then you call it an irrational number. What are the examples? Root 2, pi, and all that, right? So, but computers have only finite register. They cannot store infinite information. So, irrational numbers require infinite information. That is why we gave symbols like pi. We should actually give entire decimal expansion, right? So, we cannot give the entire decimal expansion because we don't know first. Even if we knew, we cannot write it because it is infinite digits, which is non-recurring and non-terminating. So, similarly on the computer, what it does is it chops it off. So, it will chop it off at some at about 16th or 18th decimal place. Beyond that, it is not. So that is what we do. So what I'm saying here is the calculation was performed using a 24-bit fixed point register. That means it is chopped off after 24 decimal places. So the small chopping error when multiplied by a large number, it leads to a significant error. So what happens is 110 this is the binary expansion. So a binary expansion which looks like this. So with 24, you can only store 24 digits. So that means it's only up to this. So what is the error involved? It's about 7 zeros and then 95 decimals. So if you multiply the number of tenths of a second in 100 hours, this will give you 0.3. So in other words, truncating your number up to 20 decimal place, what you will get is an error of so much. But then for 100 hours, it gives 0.34 seconds. Now in 0.34 seconds, a scud will travel about 1.5 kilometers. Which travels about the speed of scud missile, that is the primitive missile of Iraqis. It travels at this velocity, and in half a kilometer, it will get out of the range. It's about half a kilometer error. Okay? And so this that was the error involved in tracking down the. So the question now is not that you should use computer thing. When do you switch on the computer? When the war starts. As soon as the war is declared, you switch on the computer on the missile, or should you switch on the missile as soon as the enemy launches the missile? So that is the $1 million question. So these guys had switched it on even before the war, just before the war started. So which is why the error was so much. So we have a similar problem also. See, monsoon, we want to predict whether there is a good monsoon or not. Monsoon sets in June, correct? June to September. But we are seeing still the leftovers of monsoon. So, but then the government wants to know whether this year you will have a good monsoon or not in March, because that is the budget time. So then you have to integrate your equations, solve equations from January or whatever. So then in March, if you want to tell, it's not possible. The error will be too much. So in other words, your integration time or the way you calculate when there is an error in your calculation. So then the question is, how much error will you accumulate as you keep iterating? So all this I'm telling you to tell you that mathematics is playing more important role in many of these issues. So if at all what I mentioned here is not an imagination, it has actually already happened in 1991. So soon even it is now far more than 30 years now, not 25 years. So anyway, now the first thing I want to say is that functions compress information and help understand physics. So this is what Why do we study functions? What kind of functions we have studied, or what kind of functions do you know today? We know polynomials, correct? Then we know trigonometric functions, and then which one? Polynomial, yes. Hyperbolic functions, correct? Exponential, logarithmic. Which other one you said? Modulus. Okay. So modulus is just taking the positive value, absolute sign. So I'm saying which behaves in the behavior. For instance, cos and sine, tan, we know they are all oscillatory, or tan, we know goes to infinity, and similarly hyperbolic functions. So these are functions which we know explicitly. So in other words, if you say how, for instance, somebody's marks percentage in final exam from 1 to 10, are you going to give each value, or if I say no, it is exponential with a very small value, or you can say it's a constant. So that means he is not improving any further, right? So functions will help you to compress information. So let me give you an example historically which function helped us compress information. For instance, thermal radiation. So we all know that what are the three modes of heat conduction? Three modes of heat transfer: conduction, convection, and radiation. Right? In the solid, we know how given two temperatures, we know thermal conductivity. So in other words, if I want to know if this material is a good conductor or not, what you look at its conductivity. Correct? So we know that for silver, copper, there are very high values. For wood, it will be very small. So we know if you want to do heat transfer, you would prefer to use the silver material, correct? So similarly, convection also is very simple. We know we take a content of water or something in a vessel and then heat it, put it on a stove or something like that. First the container is heated and then the contents of the container are heated, correct? Convection followed by convection. And then, so we know conduction, convection examples. What about radiation? Is radiation real or is it just imaginary? Real, right? Where do we see this radiation? Mainly, every day we see in sun, correct? The sun is sending radiation from so far and then heating up the earth's surface, which in turn heats up the. Otherwise, in kitchen, if you want to see, it's a microwave oven, correct? So in the microwave oven, you keep the container inside the oven, and then the container does not get heated. Only the contents will get heated. So we know radiation is for real. Or if something is, if there is a furnace, you feel the heat. Even of course, you don't have to go to furnace. Just go out in the sun, you feel the heat. But of course, that is because the rays are hitting you. But if you stand opposite, let us say, a big rock, you will feel the heat. Correct? So radiation is for real. Now the question is, you have to quantify this. So we want to say what is the value of a radiation given some particular material. Just like we did for conduction. What is the thermal conductivity of, we know how we are quantifying this. So we will start with some hypothesis. First it says this, all objects above 0 degree Kelvin give radiation. This is from everyday experience. And it emits radiation in a continuous range of wavelengths over a large time. And the amount of radiation depends on the frequency of radiation. And the nature of the body will dictate the range of frequency. Nothing new in this. So when we hit an iron rod, it turns from black to red, orange, and then white. Correct? So that is because it starts emitting in different frequencies. So at 2000 Kelvin, tungsten emits 23.5 watts per centimeter square. That is how you measure energy, right? And then at 2000 Kelvin, molybdenum emits this much watts per centimeter square, and sun itself 1400 watts per meter square on the top of the atmosphere. So we know this. So basically what it is, radiation is a function of frequency and temperature. So here we have essentially what we have here is, it's not some discrete elements. See, because radiation is to do with liquid, gas, solid, everything. So it's a continuous function. You can't say, I can't measure thermal conductivity of silver, copper, some metals, and then make a table of that. So you see that it emits radiation continuously. So it's a sort of a continuous function. So essentially we now know that radiation is a continuous function of frequency and temperature. Because we have seen in that data here, as temperature changes, the radiation is changing. And if you look at that, as frequency also, the radiation is changing. So then, now the question is, we want to find out what that function is. Given that frequency and temperature, what is the radiation emitted by a particular black body? So we don't think of gas, solid. Suppose there is a black body which emits radiation perfectly as a function of temperature and frequency. So what is that function? People are very curious. But then it is like a murder mystery. Okay? You have some clues and you want to find who the murderer is. Right? It's like a detective story. So we want to find this function, which is a function of frequency and temperature. And we have some clues here. What is the clue? The first clue is Stefan Boltzmann. So what Stefan said was that he, based on arguments and thermodynamics and things, he said the total radiation is proportional to the fourth power of temperature. You look at now, we have a function of two variables, lambda and T. Lambda is wavelength or frequency and T is the temperature. We want to find the function, but I don't know what that function is. But if I integrate that function with respect to d lambda from 0 to infinity, it is e to the power of 4. So that was again coming from Stefan, it's called the Stefan Boltzmann law. I think you heard these names in physics class. And then the next question people ask, what is the wavelength or frequency where the maximum radiation is emitted? That means I have f as a function of lambda and t. At what value of lambda, f of lambda of t is the maximum? That was again answered by Eve in 1891. He said, I don't know that. I cannot tell you at what point it emits. But if you take the product at which the wavelength, the maximum wavelength is, maximum radiation is there at that wavelength, the product is always a constant for every week. So what he said was that lambda peak into T is always this value. This is again based on experiments. So here is Wien's law and plot of wavelength versus this, and at 300 Kelvin and 6000 Kelvin. So here's some examples. For liquid helium, at 4 Kelvin at 700 microns, that is where the maximum. So what is the product? 2800 Kelvin. And at room temperature, you see 3000 Kelvin and 10 microns, the product is 3000. And then tungsten lamp, similar, product is 3000. Sun, 3000. So approximately, the maximum radiation at which wavelength it is possible, the product is always a constant. So second clue, we want to find that function. We have clues. And for this, we got the Nobel Prize. So then, based on all this, so based on all these information, Planck proposed this method. 2h nu cubed by c square h e to the h nu by kb, where h is a Planck's constant and c is the velocity of light and kb is the Stefan Boltzmann constant. And now if you integrate this guy, you take h equal to h nu by a of t and make a change of variables, you will get this element. This is a constant, and the important thing is you get t to the 4. So this gives that radiation is proportional to the fourth power of the temperature. And this value of sigma is this. So essentially this integral should exist. And but what you see here is t to the 4. So that means if you integrate this function, remember we studied Planck's function in our radiation frequencies. And once you integrate this guy, you get t to the 4. So that means Stefan Boltzmann law has been verified. And what about this maximum radiation So P nu of t, if you want to find out the point at which the maximum radiation is emitted, so all you have to do is always a positive value. So all you have to do is find out where the first derivative vanishes. So all you have to do is put dV nu by equal to this 0. So then what you have to find is the root of this. Now how do you find the solution of this? Which I will go to. So Ax equal to, for instance, B. We know how to solve it, right? X equal to B by A. And if you have a quadratic equation, you also know how to solve it. But suppose you have an arbitrary function f of x, which can be in terms of cos, sine, or not in polynomial, right? Either we solve Ax equal to B, Ax square plus, next level is Ax square plus Bx plus C, quadratic equation, cubic equation, and nth polynomial equation. Now what is the theorem we had for polynomial equation? We had the fundamental theorem of algebra, except that you have n's, right? If you have all real numbers as its constants. But if you have an arbitrary function, it's not in terms of polynomials. Let us say e to the x, cos x, or many of these functions which we have studied. Then how do you show that it has a zero? You will use intermediate value theorem. What is called the intermediate value theorem is that if f is a continuous function and if it takes negative to positive value, you know that it will go through a zero. Correct? So that will tell you that there is a zero for it. You can't do it like quadratic equation where we wrote down explicitly the zero. You have to use intermediate value theorem to show that it has a zero. And then if you want to actually calculate that zero, you have to use some numerical technique. So anyway, that technique was used and the root we obtained was 2850. So which is very close to these experimental values. See these experimental. So approximately this, so Planck's function verified all the experimental results and verification of this function continued till 1982 with increasingly precise measurements. It has stood the test of time and Nobel Prize for Planck in 19. So here's the picture of Planck. Now, so to summarize, all I want to tell you is that this is the function. So in other words, if I want to find out that, what is the, first you consider not a normal body, like what for conduction you consider silver, copper, etc. We say that radiation of a perfect black body. It could be gas, it could be a solid, it could be a liquid or whatever. If there is a perfect black body, which may not exist, but in case it is there, so then its behavior as a function of temperature and frequency is given by this. You don't have to compile a table, correct? It's just a single line. If you have a calculator today, you can just give lambda and t. You can calculate how much radiation is emitted by a black body. For instance, sun, 1400, you will get it out of this. So, isn't it advantageous to learn mathematics and functions? Right? So, it is this is what mathematics is help, and we are able to compress information into functions. So that is my first application of mathematics. Now, here we were trying to look at a phenomenon, explicitly get the function. But then, the function may not be given, we cannot find it explicitly. The function may satisfy some equation. So for instance, I can say that the number of persons, human beings in this room, each time we will count and then, but suppose I know from where they are coming. They are all either coming from that room or that door or coming from some other door. So I am observing that they are all coming from this room. So then I say that the number of people here is the number of people coming through that door. Right? So I just write an equation based on this. Conservation of number of people, either it is increased or decreased by this. I will not give an explicit function of x, but if there is a function like this, it will satisfy some conservation. And we have to solve that equation to find the function. So it's just in case of Planck's function, what it is just guess. Experiments, guesswork, and then verification. Okay? So first you observe the phenomenon. Based on the phenomenon, you make some guesses, propose a formula, then go back and check the formula whether it is true or not. So in the the function was proposed in 1950. People are not satisfied. People went on to check from 1950 to 1982. Only after 82 people stopped checking whether this function is correct. So, but if you want to, you don't have to take it so long, but you can just write a principle for that function. So that is what differential equations is all. So differential equations is again, you have to find a function, not explicitly by making measurements or observation or guessing. The law is given to you. You based on that law, you write down a relationship between the functions, and that function you solve. That equation you solve. That is what is called a differential equation. So, for instance, if you have I already mentioned this to you. From here, you have in between many polynomial equations, and you solve everything. And similarly, what is this? X is not a scalar. X is a vector. Okay. So then you solve a matrix equation, and again you can have a function which is where X is now a vector. It's a map from Rn to Rn. So similarly, if you have a differential equation like this, dx by dt is again you can solve this explicitly, e to the t into xe. That is because the derivative of the exponential is exponential. Correct? The exponential function e to the x is 1 plus x square by 2 factorial and so on. So if you differentiate this, assuming that the series is okay, then again you will get back the same series. So the derivative of the function is itself. And that will give you a solution which is like this. So suppose I say, what does xt correspond to? Xt corresponds to displacement. I say that at t equal to 0, I am at this coordinate. At time t equal to 1 second, I am moved here. So I know how much I am. So xt says distance moved as a function of time. What is dx by dt? Velocity, correct? So if I say that the way this particular motorcycle is moving, it looks like it is moving as fast as it is, the displacement is as fast as the velocity, as long as the velocity. So that means what velocity and displacement are proportional to each other. Okay? So that is what this law says. But I don't know what that function is. I am just saying that the displacement and velocity are proportional to each other. I just find the proportionality constant and fit that somebody has to give you A. You just have to find what proportionality constant, and then this solution is fixed by this function. So similarly, you can have a matrix also. Here now x is a vector and A is a matrix, but still you will have exponential of e to the a. You can define an exponential of x. If you can define an exponential of a scalar, you can also define an exponential of it exactly in a similar way, so long as A is a square of x. Now, again, a similar thing like Planck's black body function. Now, here again we can't find the function, but we can find the expression or the differential equation which solves it. This is Kepler's planetary motion. Now, what did Kepler do? Just like people observed radiation, this person, Tycho Brahe, who was a Danish astronomer, he went to an island and positioned himself, and for the whole life, he was recording the position of planets, Venus, Mars. He took a book and then recorded that in that big book, okay, some 10 big volumes. Okay, every day where the position of Venus was, Mars was, okay, like that. Now, again, we don't want this huge. Who will look at that huge volume, right? And in India also we used to compress information. How did we compress information? In terms of shlokas, correct? We always wrote 2-line shlokas. And that some guru or Sanskrit guru will teach us what is the meaning of those shlokas. So we have everyone wants to compress information. So similarly here the planetary positions was in terms of huge voluminous data. Now Kepler came and looked at that data, and he said that we can reduce it to 3 laws, again which we have studied in our physics classes. And that is the orbit of Mars is an ellipse, with Sun as one of its foci, and the line joining the planet is sweeps of equal areas, and for any 2 planets the ratio of the squares of their periods is the same as the ratio of the cubes. So who is Johannes Kepler? He was a German mathematician. physicist, astronomer, and he worked under Tycho Brahe, and it was based on observation scale. And he is considered to be the founder of celestial mechanics. But then Newton comes in, and then he looked at these laws and maybe a little bit of data. But what was his data based on? He was sleeping under a tree, and he saw the apple fall down, right? And based on that, he proposed this. So everything happens as if matter attracts matter in direct proportion to the products of masses and inverse proportion to the squares of distances. Now again, just like in the beginning I told velocity is proportional to displacement, Newton said that general law is force is equal to mass into acceleration. So if you call x t as displacement, x dot t is velocity. What about x double dot? dx by dt is velocity. d square x by dt square acceleration, right? Acceleration. So Newton said force equal to mass into acceleration. You reverse it, mass into acceleration equal to force. That means m times d square x by dt square equal to some f. So if you know the acceleration and if you know the force, all you have to do is give the proportionality constant. Then you will get a differential equation which solves this, which sort of says about this law. All you have to do now is find the solution of this. So he said, he just gave a law. What happens? He says that if there are two bodies, astronomical bodies like this, when they come near, they repel, but when they are far, they attract each other. So that means you have to look for a function which is infinity at 0 and 0 at infinity. What kind of function is that? Can you think of a function which at x equal to 0 it is infinity, but as x goes to infinity it is 0. 1 by x. Simplest thing you can do is 1 by x. Correct? As x goes to 0 it goes to infinity, and as x goes to infinity it goes to 0 for x positive. Right? So that is what he did. So he wrote 1 by x. So here it is. I'm sorry you can't see this properly. If you have n bodies, k equal to 1 by n, xk double dot. That means it is d square xk by dt square. So all we are writing here is mass into acceleration equal to force. So the force is given by this gradient. What kind of force? Newton said the force is like by just looking at the apple falling down. He said when it comes near, it repels. When it goes far, it attracts. That means it is like 1 over x. So that is what he said, like 1 by x. It's slightly complicated than 1 by x in the sense that it is norm of xi minus x2, but it is a glorified form of 1 by x. So now the question is, what kind of portions are possible and why? And is the solar system stable? So let us take n equal to 3. The sun, earth and moon. These are the three bodies. And then each of these bodies have three coordinates, x, y, z. Right? And then we want to know what kind of trajectory it pursues under this force. Now, what is the force between sun and moon and earth? It's the gravitational pull. Correct? So mainly if you know what the gravitational force is and you write down this, that means you must get these orbits as your solutions of your equations. Right? So that is exactly what Newton proposed. So then, is the solar system stable? What is stability? Stability means if I make a small change, then the solution should not change much. That means it is like if you say in cooking, I add slightly more salt, the taste should not change. Everybody say add, that's why they say add salt according to your taste. Right? They don't say how much. If you say half teaspoon, you get more. But suppose if you have half teaspoon, I add a plus 0.0001 gram extra, the taste should not become totally different. Correct? So that is called stability. So I make small changes, the thing should not change. Like parents also with children, we want our children to be religious, but not so religious they go and join some math, right? Just religious enough, you stay in the home and do puja and respect the parents, right? So don't go away to a similarly, in Bollywood also you will see that one twin is born few seconds after the first baby, correct? First one, the baby is born, the next twin comes a few seconds after. One becomes a dacoit and another becomes a police officer. Correct? So, if this fellow is born only half a second after the police officer. You should also become a constable at least. But then he becomes a dacoit. So that is instability. So what we want is stability. Small changes should lead to small changes in the solution. Small changes in the data. So what is the data here? The data here you have is masses. If the mass changes from 10 kilograms to 1 kilogram, the solution should not become very indifferent. You should have small changes in the solution. So if you have two-body problem, then you can easily solve it. So you have an equation like this. So this is d square r by dt square, r d theta by dt square equal to 1 over r square and so on. This is a coupled equation, just like you have a matrix equation. Then you have to solve this. I will skip the details, but what it gives is that you can have three kinds of solutions. One is circular, elliptic, hyperbolic or parabolic. So when you have here this, either it's circular, elliptic, parabolic or hyperbolic. So if you have a parabolic or hyperbolic, that means one of them is escaping to infinity. So that means what is this saying? It's telling us that suppose you ignore moon, there is no moon, let us assume that there is no moon, only sun and earth. So these are the equations. We know the masses of sun and earth, somebody has already calculated it, and then you put the initial position. Now instead of making measurements, you solve this equation. If you solve this equation and look at it, there are four kinds of solutions possible. One is circular, elliptic, parabolic or hyperbolic. Of course, circular is not, by looking at the masses, you can say that the solution is always elliptic. So it's a great success of these equations. But physically, what does it mean if you are parabolic or hyperbolic? It means the earth is escaping away from sun's gravity. It is not rotating the sun, but it is moving away somewhere else. It is escaping to infinity. So whether that is possible or not, you have to look at the parameters. So that is what. But if you have three bodies, the solutions look very complicated. So it looks, it is nothing like elliptic at all. So that is what, here how the equations look like. So each Ri has three coordinates, x, y, z. Each body has three coordinates, x, y, z. Correct? And then the double derivatives are, there are three equations here, three second order equations, three here and three here. So there are set of 9 set of second order differential equations. So that is what it is. So then this person proposed a series solution for these equations. Now these equations are extremely difficult to calculate. It's impossible to get a solution for this because n equal to 3 is whereas two bodies, if you include the moon, then the solutions change very drastically. So here is what he wrote in French. I will skip this. So then now this question, namely this person wrote down a series solution. Now you must think that what are all the tools that we have to solve any equation? That is extremely complicated. But those three computers are available, but then you can also write in terms of series solution. Especially in those days, people wrote solutions in terms of series. Now here is a problem that we face. I told you about accuracy in the beginning, besides how accurate they should be and all. Now suppose I have an infinite series. Now how did we define convergence of an infinite series? We took partial sums, correct? We took partial sums and made it into a sequence, right? We know when a sequence converges. If successive elements are less than epsilon, then you know that sequence will converge, right? Which is a sequence which does not converge, minus 1, 1, minus 1, 1, like that, right? That is oscillating and it never converges. So we know what a sequence converges. Now series, if you want to know when it converges, you make it into a sequence by looking at partial sums, right? You look at partial sum. What are all the tests you have learned for series convergence? Ratio test, number test.
They don't have something.
Oh, they don't have.
They don't know about the convergence and divergence.
Oh. So anyway, you have an infinite series. Then what you have to do is, I want to truncate it up to some point. So then, where do you truncate it so that you get some particular accuracy? So that is what this is saying. That it will be, the convergence will be too slow. And if you want some accuracy of 0.1, then you have to take 10 to the 8,000 terms in that series. Okay. So that is what numerics is the only way out. So you have to solve them numerically, and you can get all these kinds of solutions. So anyway, before I come to this, I want to summarize what I've been trying to convey. So what I'm trying to convey is, first thing is, functions will help us compress information. I give you the example of Planck's function. Thanks to that, we are able to compress the radiation. Now, next thing I'm saying is that these functions you cannot determine experimentally. Like for instance, suppose I ask you to measure temperature over the ocean. It's not possible, right? Somebody can't go in a ship and then keep measuring temperature at every kilometer on the earth. So for that, what you have to do, you have to describe some law. Okay? And that law is expressed in terms of a differential equation. And that differential equation, if you solve, hopefully that solution of that differential equation will tell you what that function is. See, for instance, Planck's function, we looked at measurements and then made a fit to that function. Guess. It's purely intelligent guesswork. And then somehow it worked. But that may not work all the time. So if you want to do this in a systematic way, Planck's function should come out as a solution of some law. Okay, that law, it turns out, is very complicated. You have to go to quantum mechanics and all that. But it is like tossing the coin. See, what about tossing the coin? Again, I want to say heads or tails. What do you do in that case? Either you write down the Newton's laws of equation and then say what is the position of the coin and how much force you are imposing on your coin, so that you can predict it's going to be heads or tails. But then those equations are so complicated that it's better to observe how many times you will have heads and how many times you have tails. So what mathematics tells you is that given the initial position and velocity, we cannot tell whether it is heads or tails. But if you toss 100 times, 50 times will be heads and 50 times will be tails. That's all you can say. So this is what I'm trying to tell you there is that in the case of planetary motion, one person actually did the measurements. Okay, that is Tycho Brahe, and then those big voluminous data was compressed into 3 laws. Just like we do entire Mahabharata, Ramayana, people will tell you 2-3 slokas if you want, right? So if you go on writing each and every thing, it becomes voluminous. So Tycho Brahe did make these observations. Kepler reduced it to 3 laws. Newton came and proposed a mathematical equation, mass into acceleration. And those equations are these equations for a 3-body problem. All I am trying to tell you here is that these equations are extremely difficult to solve. So if you want to solve these equations, you better learn differential equations and function theory, Fourier series, etc. Because I am told the major question is everybody is asking, why should I learn math? Correct? If you don't learn math, what will happen is you will have to be dependent on foreign technology. Because they would have learned math. I told you just now the example of lung cancer and tumor. Every time you have to depend on either Europe or America to give the machine, and then the algorithm which goes into that, they will not tell you. It is all based on mathematics. By the time you understand, you said, oh, I've forgotten all my mathematics. This is a standard problem story I have heard from many people. So in order to convince you that it is worthwhile to study mathematics and where mathematics is used, I am trying to tell you these examples. Okay? So you may feel bored, but then if you want to be relevant, then it is better to take your math courses seriously in your class. Okay, next I want to tell you is about projectile motion. Okay, I gave you a very complicated example, this complicated equation here. But then, what is the simplest thing you can solve? Is the projectile motion, which we all studied in our class, in high school. So what is it? So if you again is the same problem, namely m d square mass into acceleration equal to force. The only force that is acting is gravity. Right? So once you have gravity, this is just a constant, and you can easily solve this. If second derivative is a constant, you know what the function is. You will be quadratic, right? if f of x equal to x square, f prime is 2x and f double prime is 2, right? So if second derivative is constant, it will be like a quadratic. Then this is what you get t square. And so we have the solution, namely if your initial position is at 0, okay, at x and y, and your initial velocity is given in terms of mod v0 and sine. Alpha is the angle at which you are throwing. This is the angle at which you are throwing. The velocity component is divided into 3 components. So now, after you solve this, what is the question that we have asked ourselves? We asked what is the maximum range, right? So here it is. The projectile reaches its highest point when its vertical velocity component is 0. So you have to solve this equation. And what you got is the time. And once you plugged in the time, you got the total time. Once you got the total time, you looked at the range. The range was v0 square by g sine 2 alpha. Now when is sine 2 alpha maximum? When sine 2 alpha is 1 or 2 alpha equal to 90 degrees. So we all learned in our school that if you throw your projectile at an angle of 45 degrees, so then you reach the maximum range. Correct? That is the maximum range you get. Now, when you actually go and do it on the field, it is never like this. It is 45 degrees is not the angle at which you get the maximum. Now, what is the reason? The reason is you have missed something, and that is friction. Just like here, suppose I am trying to model the number of people in this room, and I see how many I've counted here. I see that 100 have entered, but when I count here, there are only 90. What happened to the other remaining 10 people? Okay. So then I don't know that there is a secret hole there by which people are escaping. Right? From looking here, I say that, oh, 100 people here, but there are only 90 guys here. So that means I missed some information. Missed the fact that there is a hole there. And so similarly here, the angle you throw at 45 degrees and you don't see the maximum range. That means you have missed something. What is that you have missed? You have missed air resistance. So we have to include air resistance to do that. And what is the air resistance will be in terms of this form. Now why I am saying A times dr by dt, I am saying that resistance is proportional to the velocity, which is true, right? I mean, you go in your motorbike or in a car and keep your hand out. The faster you go, the faster you feel on your hand, right? That means as the velocity is large, the friction will also be large. So we use a very simple model, namely K times dr. Of course, we can have a general non-linear model, but we will not use it. In that case, what happens? You get into a very complicated equation. So in this case, the maximum, if you want to find the maximum time, you have to solve an equation like this with W, which looks like this, W of x. Goes to 0 and then comes down, and it is the inverse of this function. So earlier, to find the maximum time. So here, how did we get this? We just got t equal to 2u0 because we just differentiated this guy and then found the value of the roots, 2 roots over there, right? There are 2 roots for this guy. So it's a quadratic equation. Either t equal to 0 or this quantity is 0. So in this case, you got 2u0 by. So this is the time at which things came. But that is because you did not include the friction. Just d square r by dt square equal to minus. But as soon as you include the friction, then to get t, you have to solve an equation like this, which is extremely complicated. So even if you were to, anyway, I skip all this and I'll just give you the picture. So in case you add friction, it becomes extremely difficult. Now this is okay when I was studying. It was about 30 years back in high school. But today, you are not at the same level as what I was in high school because you have some extra gadgets in your pocket and in your bag. What is that? You have a laptop, you have a mobile, right? And you can easily calculate this. But still, we don't use this. We are using all our laptops only Facebook, WhatsApp and all other things. You can solve these equations very easily on your laptop, provided you are willing to use mathematics on your laptop. The thing is, we are only watching movies and other things. So, in other words, you are learning the same thing as what I was learning 30 years back, even though you are having all modern day technologies and gadgets. Or even earlier, even what my grandfather was learning the same thing. Why? Because it is very easy. This part is so easy that you can, when there is no friction, all you have to do is simply calculate what is the t here. Do you need a big calculator here? No, you don't need. But when you come here, you can use your calculator and you can come up with a plot like this. What is this plot? This plot tells you how the range varies with theta for various k's. What is k? K is the proportionality constant. So k is the, here is this k. Now I want to look at various k's and various angles. So I change the friction from 0.1 to 4, okay? And then I look at what is the maximum range achieved at these angles. So, for instance, if this pi by 4 is for very small k, for almost k equal to 0, that is our original case. But as you keep increasing friction, you better throw it at smaller angle. So, in other words, you'll say, so what? Who cares about this? Then the question is whether if you are a fielder, if you are fielding in Jodhpur or if you are fielding in London, you have to change the way at the angle at which you throw to the wicket keeper. Correct? What's the difference? Because in Jodhpur it will be very dry, right? Whereas in London it will be the weather is always wet and the friction will be more. Correct? So it is if you are so it has some practical value. Suppose you want to do much more. You want to predict trajectory. So here I am talking about a rotating spherical. Here is a sphere which is having all this. Have you heard of Magnus effect? Yeah. So Magnus effect, again, who uses it the best? Best is the off spinners. Okay. So when the off spinner is going a top spinner, okay, what happens is when the trajectory is suddenly curves down because of Magnus effect. Correct? So which is why the batsman who is facing the top spinner feels that he can go for the drive, but actually the ball would have fallen much before, and so he will give a catch. Right? So that is what is the Magnus effect is good for top spinners. So you can include all these things. So for instance, here how to measure friction. What you do is you take a rotating sphere and put it in the wind tunnel, and you will see that in this case the friction is more, whereas in this case friction is less, okay, depending on the angle at which the seam is facing. The angle seam is facing like this, then you will see that, whereas here the seam is in this direction. Here is a smooth surface, so friction is less. Okay, so what I will skip all the details. All I want to tell you is you can couple these three equations, x double dot, y double dot, z double dot, into these complicated expressions, which I don't want to go. And these expressions itself can come from by solving these equations. So which is again more. But anyway, let me show you the figure. So what is the effect of drag force and presence of the wind on the trajectory and range of a cricket ball thrown from the boundary with an initial speed of this at an elevation angle of 25 degrees? So this is the initial position, and then this is with drag means friction, with friction included, and the spin is either rotating or counter-rotating. In each case, it misses by this. So yesterday you have seen Jadeja able to throw very quickly. His reaction time is very swift. So these things can be calculated from this kind of figure, where this is a side view of a cricket ball trajectory, and then this is a top. So in other words, all I am trying to convince you is that you can. The most complicated, which you cannot observe, is planetary motion, and then the simplest is projectile motion with just gravity, and then you can include Magnus effect, gravity, friction, plus the velocity itself coming from some other equations. So this So in other words, if you want to make these accurate calculations, you will have to solve differential equations. So then this is what this part of my talk is conclusion is that basically mathematics is useful in compressing information. And that information in terms of functions. And that function can be explicitly measured and fitted either through a fitting procedure. You don't do any physics or you don't put any physical concepts into the fitting. All you do is just a pure, I want to fit a quadratic function to this data. I want to fit an exponential function to this data. Or you can say, I don't know what that function is, but that function satisfies some law. Like Newton's law. Force equal to mass into acceleration. Now, it satisfies this law, so I solve these equations and get the function. So this is what this is the basic philosophy behind math of functions and differential equations. Now, finally, I want to conclude by giving an example from my own experience with an Indian context. So this is what is called the lifted temperature. So what is the lifted temperature level? So we all see in our papers, as I already mentioned, the maximum. What is the weather prediction you get? Partly cloudy. Maximum is this, and minimum is this. Correct? So, but then we don't know where it was measured and at what time it was measured. Right? So usually it is measured at the airport or the weather Met office at midnight and noon. That's what it is. We don't give a measurement even for each area in Kerala. So it's only at the airport. But of course that is good enough if you think. Now, already mentioned here, where and when it is measured at about 1.2 meters, 2 times. And then what is the general belief here? Belief here is that the air temperature is TA and Ts. During the daytime, surface temperature is much larger than the air temperature, correct? That's what we wear footwear to walk on the streets during the daytime, right? Especially the surface is very smooth. We are not having thorns or stones. So then you use some footwear because this is very hot compared to the air. Air is not so hot compared to the surface, correct? During daytime. So on the other hand, it is the reverse during the nights. Now, what about the temperature as you go up in height? So it keeps. So what the plotted here is temperature, and then this is the height. So the height is as you go in height, the temperature decreases. Is there any evidence for that from your day-to-day experience? When you keep going up, the temperature decreases. You go to any hill station, correct? You feel you go to Nandi Hills or you go to Tirupati or this side Mathena or Gunnar in Kerala. They are all very cool places because they are located at a very high height. Or if you are flying in aircraft, the guy will tell you that outside the temperature is minus 40 or minus 20. So this is at 10 kilometers you have what is called the tropopause, and aircrafts are flying between 10 to 12 kilometers. So the temperature is usually decreasing up to some point, and then. But if you close at 100 centimeters, which is about 1 meter height, then it's the same. During daytime, the temperatures are whatever I said here, namely ES is bigger than EA. So what you see here is much larger at 2 o'clock, for instance. The ground is the warmest and then it decreases. So all these black lines. And similarly during night time, the ground is coolest and then it increases. So either it is monotonically decreasing or increasing. To summarize, we can say that during afternoon the ground is the warmest and then it decreases. And then during night the ground is the coolest and then it increases. So this we can, this is from day-to-day measurements and experience. And then as I already said, functions help you to compress information. And for the temperature you can say that it is z to the alpha, alpha is negative during daytime and alpha is positive during night. So for instance, if you take the square root of x, it is increasing like this, and x squared, but the derivative will be infinity as z goes to 0. But then, so this is what the impression you get as soon as you observe day-to-day temperature. Now, if you, two people in India found that it is not true. For instance, in Pune and Agra in 1931, at 6 o'clock in the morning and 5:30 in the morning, the ground is at the warmest. The ground is at the warmest, and then it decreases and then goes like this. Similarly here, the ground is at 80, goes down and then decreases. So this is how the temperature looked in 1930s when this was measured by two people called Ramdas and Atmanath. Now what will you do when, as soon as you see this temperature profiles, when you are brought up with this kind of observation, you always see that the ground is the coolest and then it increases as it goes up, correct? And when you see this kind of a profile which is reverse of this, namely what is happening is it is here and then decreasing and then only it does this. Does like this and then this, not like this. So as soon as you observe this, what will you say? Obviously you will say that, oh, this must be something wrong, correct? Either the experiments are wrong or the guy who observed it must be faking it, or it's not believable. The result is not believable, correct? Because from day to day experience, okay, suppose you didn't have bias on the person, then why these results are not believable? Again, because of stability. As soon as you heat air, what happens? It raises up above, correct? Because the density gets reduced, and so it becomes less dense, and so the air rises up, correct? Just like all these hot air, if you see when you heat a container with water, then you see that as soon as it becomes hot, it raises up and then comes down, right? And so when the fat goes up, it cools and then forms a solid, and then the layer is formed. Right? So this cannot sustain itself for so long. The instability has to come in and then mix up. How can you have an unstable layer below a stable layer? So these results are not believable. So that is the first thing. So now this was observed by two people called Ramdas and Atmanathan. They were working in the Indian Met Department in Pune. And so who was Ramdas? He was a student of C.V. Raman. He joined the Indian Met Department in 1920. And this was called as the Ramdas. So what are the reasons for him studying nocturnal temperature? Here's a picture of Ramdas. So the reason why he was studying this Ramdas, this kind of nighttime temperature profile, was because at 1930s we were still under the British. So the British government said that no independent research during office hours. So he said, okay, then I will do research during nights, non-office hours. So he was observing this. So obviously these results were not believed, but then finally one German came, his name is Raschke. He came to Pune and then he spent a lot of time in this field where Ramdas measured there. And he brought his own thermometer and then he made measurements and he found that what he did was correct. What Ramdas did was correct. So for more than 20 years these were not accepted. And then he spent 3 years with Ramdas making measurements. And he made measurements for 183 nights. The phenomenon is stable and persists. So there is no doubt about that. So similarly, the last observation was done in Canada, and it was. So here is the chronology. So first time in India, second time in US, and so on, up to 1917. So this was called Ramdas paradox: lifted minimum, raised minimum, elevated minimum, Ramdas effect, Ramdas effect. So there were many explanations. I will not go into the explanations. So all of them are mutually contradictory. So one person says it's called is a purely radiative phenomenon. Other one says it's a purely turbulent. That means convective, purely convective. So now we come to another application of mathematics. That is, we have observed something which is not normal. Now, but that is confirmed. And then we know that heat transfer is in 3 different modes: conduction, convection, and radiation. Now each of these people who made measurements are saying that this is all because of convection. Another person is saying this is all because of radiation. So what do we do then? Who is correct? Right? So again here mathematics comes to the. So that is what somebody was saying. Can we set up differential equations in order to discuss whether values can be given to the parameters to permit the observed points to. So that means if you say that it is radiation, then you please solve the corresponding differential equation, and then or you do experiments. You can also do experiments. You go to a room, avoid all conduction and convection. Make sure that only radiation is present, just like projectile motion. See, projectile motion, we said that if you want maximum range, you have to throw at 45 degrees. So if you want to verify that, you have to do it in vacuum. So what do? We make this room completely vacuum and then throw the ball and check whether alpha equal to 45 is correct or not. Because if you actually do it in the field, you have to include air resistance. Correct? So similarly, if you want to say that one particular phenomenon is particularly causing this particular profile, then you have to eliminate those things and do an experiment. Is that costly, or putting up differential equations and doing it quickly is easy? Right? That is more easier and sort of justified. So which is why these people say this. So now you may ask, why do you bother about such things? Such silly things, correct? Whether the temperature profile has minimum at surface or at the level, who cares? Well, we didn't bother about surface tension. Whether the surface wets like this or the other way, we did make studies. And then there seems to be applications in agriculture, especially when the flower to seed formation, the thermal environment around the flower should be conducive for it to form the seed. So if you see here, these things have been damaged, whereas these guys are healthy. The ones above 0.5 are healthy, whereas all the guys below, the flowers have got damaged. So there is some application. So I will not get into all these things. So we put up differential equations and then calculated all these things and showed that it actually predicts these things. So, but we can actually make a simple example. So here is a function in differential equation which says that there is an epsilon which is very small, delta is also very small. Then if you put lambda equal to 1, 1 is a solution. But if lambda is less than 1, then you get a solution like this. So in other words, using mathematics, we were able to solve the problem that who is right. So what I mentioned to you now is the use of mathematics in also resolving some controversies. So let me come to another example. Now, is it really true? These two slides are taken from Boeing. Now, what happens is when you design an aircraft, yes. Just two more slides. So one more direct, very important application, which will tell you the importance of mathematics, is the design of aircraft. So what happens is when you design build an aircraft, first you design the fuselage. That is this particular thing, the wing ones. This entire thing is fuselage. They will first design that, and then they will design the wing. So based on this structure, they will decide which wing is correct for that particular model. Now, in the early days before mathematics was very strong and computers were very strong, they used to test about 77 wings. Today it has come down to only 11. So what they would do is they build the body first and then test 77 different wings, put it in the wind tunnel and find out which is correct. Today they have reduced it to 11. How this reduction has happened? Because of computers and because of mathematics. So the message is mathematics is very important. I already told you there is a World War philosophy about mathematics. Already the example is there. Okay. And apart from that, it is all data and information. If you want to handle too much data and information, mathematics is the only way around. So there are a lot of hidden mathematics going into many of these gadgets, which people will not tell you, giving you a feeling that you don't have to take math seriously. That is also wrong. Okay. So that's all I have to say. If you have any questions, tell you is Indian mathematicians are more on to rituals and things like that. For instance, they did not bother whether root 2 is rational or irrational. There were no Euclid axioms. So most of the time, because ours is based on rituals. So Rahu Kalam is going to go. So you take root 2 as 1.414 and proceed with the rituals. Don't bother about whether it is rational or irrational. But why he did, I don't know.
Sir, now whatever the equations you show now,
Yes.
it's totally invented by Planck's Newtons. So they invented in their own language, in a foreign language. Can we make them into our Indian language and make them full easy
No,
equations?
mathematics is a language.
In foreign language, we should make it into Indian language. It will be very easy to solve. We solve the foreign language because foreign people invented all the equations.
Yes.
So, can we make it Indian, like all lambda and all it came
No,
from
but
foreign?
you are not able to understand it now?
Sir, what?
No, you are not able to understand these equations now?
Sir, it's not there in our syllabus.
Okay, whatever is in your syllabus, because it is in English, you are not able to understand. What is in your syllabus? Tell me, what is the last thing you have learned in mathematics, the last class?
Sequence and series, trigonometries, permutation, combination,
So give
complex
me one example of a sequence. Give me one example of a sequence.
Tn equal to a plus n minus 1b.
Okay.
So
But
that-
it's arithmetic progression. Okay. Now, you want to say this in Indian language? Or?
So now this is the other land, others are there.
Okay, no, people consider mathematics itself is a language. So mathematics itself is a language because you are expressing some physical quantities in terms of some expressions. So, in fact, some physicists call mathematicians as linguists. Yeah, if you can want to learn it in Indian language, that is perfect.
So, why do we use pi value as 22/7?
Is it rational or irrational?
Irrational.
Yes. So we want we want to compress information. No? So what we do is, what is the best approximation to pi? We can't, suppose you approximate it. 22/7 is the best. There is also what is called square root of 10 also is there. Now anyway you know the infinite expansion up to at least some 20 decimal places you know. For instance, you can use also 3.14. So 314 by 100 also is another number, approximation.
Sir, in circle, we use to find circumference or area, we use pi value. Why should we use pi value there in circle?
No, see what has happened is the ratio of this circumference to perimeter, right? So that is always a constant, whatever size you take. So that constant turns out to be pi.
Thank you, sir.
It is a reverse. Chronology is a time ordered sequence. You take any set of numbers, what happened first, then second, third, in time wise. If you order a sequence time wise, you can say it's chronological
Thank you, sir.
in terms of time.
Rapidly increasing. So, can it be that in some time out in the future, the information increases so highly that we cannot even store it, or we could not go further?
Yes, explosion of information is there, but then the devices are also getting more and more what you call finer. So yes, the information that's what they call entropy. The entropy will have the information is always increasing. So when you keep increasing the information, then the disorder is also increasing. I don't know I answered this correctly. Information, yes. Only I can give you a side example, namely that people all over the world what. It turned out that the way Indians store Vedic knowledge is the best way. You keep uttering Vedic mantras, right? Those people don't know the meaning. They are only storing the Vedic mantras. They're chanting that so as to preserve it. Because every sound, every syllable, every consonant, everything has to be uttered precisely. Correct? So, storing this is a side answer. I'm not able to answer your original question precisely. But all I'm trying to tell you is the Indian way of storing knowledge by memorizing and passing on to successive generation seems to be the only information which is stored for very long. No other religion or anywhere has stored information like what we have stored in our Vedas. So similarly, when you calculate fluid flow past any body or anything, there are equations. You can't solve them explicitly. You will use computers to solve those equations and then predict what kind of flow. There we solve those equations and predicted whether the motion is circular, elliptic, or hyperbolic or parabolic. For an integrated MSc mathematics in many of these IITs or ICERs. ICER Pune has an MSc mathematics 5-year program after plus 2, and then BMath is there in ISI, Indian Statistical Institute. That is also after plus 2, and BStat is there. I'll tell you one secret: whoever does BStat will get more jobs than an IIT computer science graduate. It's a well-guarded secret. It is done only in ISI Calcutta. Nowhere else they offer a BStat course, Bachelor in Statistics. Now statistics and information science are the most sought after disciplines. So if you do a BStat, you will end up with many jobs after your BStat, all these multinational banks. Plus, of course, you can also pursue a research career in statistics. So these are many of the career options. Most of the people are looking for nowadays mathematics graduates because they are thinking if you are trained logically, what mathematics helps you is thinking logically. It doesn't matter what subject you move after a bachelor's in math. You can tackle any subjects because you will have this structured way of thinking and logical way of thinking. That is what mathematics helps you. So if you ask me, even if you don't do all these applications, okay, as a human being, as a personality development, it is good to learn mathematics because it helps you in structured, logical thinking. This is very important if you want to be a successful human being.
Thank you very much, sir. It was really interesting.